let's pick up from where we left off last time. So we had the Pauli matrices, and we defined this multiplicative group curly P, which was the tensor of n Paulis with some coefficient out in front to make it a group, because we noticed that, for example, x times y is r times z minus r times z. So we need some plus or minus 1, plus or minus i's in front of it. And to make our Stabiliser code, we were looking for an abelian subgroup. So we had took some abelian subgroup of P. We added the condition that minus the identity was not in S because we wanted to find Q of S to be the joint eigenspace of eigenvalue 1 of the elements S. So this minus 1 identity not being met is just to avoid trivialities for our stabilizer. So this is our stabilizer, this is our abelian subgroup. So essentially what that means, since all of these have order 2, okay, so they're x squared is the identity, y squared is the identity, and z squared is the identity. Effectively what that means here is the C for the elements S. So let's write something like M in S implies N is plus or minus sigma 1. Oh no, hold on. Okay. No, that's not true. No, what I want to say is that so we can define S by second generators. Define let's call those M1 to N minus K. And so since where we choose these generators so that N squared is the identity. So that we can think of just taking the N's to be the tensor product of N Pauli matrices. And since it's abelian, so since it's abelian, this implies size base is 2 to the N minus 10. So the elements of S precisely take a subset here of N1 to N minus K, and you will get elements of S. Okay, so the first and important theorem that we're going to do today is that the dimension of Q of S is 2 to the K. And to prove this, we're going to use exercise 6.2 first. So we define P to be the 1 divided by the size of S, the sum over all the N in S. Now, we will prove in exercise 6.2 that E is the orthogonal projection project them onto Q of S. And that more or less, I mean, a few things from the local assignment exercise. You can prove that for all, let's say, so let's do it here. So for all n in S, you can prove that n times p is just p is equal to p times m. And then from that, you can prove that that's equal to p squared. Okay, so you prove that it's projector. P squared is equal to p, and then, yeah, and then, well, so that's a clue as to how to go about proving that. But knowing that it is the orthogonal projector onto S, well, it's a projector, so p squared is equal to p. So I'm now going to assume exercise 6.2 is being done for us. P squared is equal to p, so that implies that the p has eigenvalues 0 and 1. And so the image of S, so the image of P is Q of S, since P is the orthogonal projector onto Q of S. But the image of P is also the eigenspace of eigenvalue 1. So everything else is in the kernel. Everything else really, I mean, the direct sum of the eigenspace. The image is the eigenspace of the eigenvalue 1. So what's the dimension of the eigenspace of eigenvalue 1? Is equal to the dimension of this eigenspace, which, well, the dimension of the eigenspace of eigenvalue 1, of course, will be the sum of the eigenvalues. Because the eigenvalue is 1, and that is equal to the trace of P. Okay, so the diagonalization, that's kind of more than 1 and more than the trace. So now we have to calculate what is the trace of this operator. Now the trace is additive, so we can sum up the traces. So what's the trace of a typical n in curly P? Well, let's just think about the trace of the tensor product a moment. So what would be the trace of A tensor B? I mean, in that case, it's going to be these are going to be 2 by 2 matrices. But well, that's going to be A11, so it's going to be the trace. If you think about this in its matrix form, then this is just going to be A11B, A12B, A21B. In fact, for us, that's exactly because it actually 2 by 2. So then when you trace this blown up matrix, you're basically getting the trace of A times the trace of B. Because you get A11 trace of B, A22 trace of B, sum them all up. And you get this. So this implies, what does this imply for our M's? So for M equals sigma 1, trace of this M is the product of the trace over sigma i's. But the sigma i's are all Pauli matrices. They're either 1, x, y, or z. And the trace of x is 0, the trace of y is 0, and the trace of z is 0. So this is going to be 0 unless trace of unless sigma I is the identity for all y. So the trace, so going here, trace of P, this implies trace of P is equal to, well, the trace of all these things is 0, apart from the first one, the trace of the identity element. Now, this is the identity element acting on our Hilbert space, which has dimension 2 to the n. So the identity matrix here is a 2 to the n times 2 to the n matrix. So this is 2 to the n divided by the size of s. And the size of s is 2 to the n minus k. So the trace of Q is in fact 2 to the k, which is what we wanted to prove. So if you recall last time we saw an example and we had on our 5 cubic space, we had S generated by 4 operators. So, and I told you, well, the dimension of the code is 2, and at that time we just have to accept it. But now we see that indeed it is 2, so we can have a 0 logical bit and a 1 logical bit, and encode at least 1 qubit onto 5 qubits. So we're encoding 1 qubit on 5 qubits, and we could correct 1 error. So that was so we normally write then so S for S size 2 to the n minus k, Q of S is a N K D. And we put these double brackets to a single bracket to be a non-classical linear code. So when you see NKD, this K, the actual dimension of this thing is 2 to the K. Okay? The N is the number of qubits you're mapping onto. So you're encoding K qubits onto N qubits. And the D, where D, if we recall, D was the minimum weight of the elements in the centralized ones, not S. So we call that the centralized with all the elements of the Pauli thing which commute with all the elements in S. Okay, so that kind of finishes off 6.3. And now I'm going to explain the link between, which I promised you last time, the link between stabilizer codes and classical codes. It's classical binary codes. Okay, so. Stabilizer is one of those words that I can't write. Oh. so the idea is whether we can actually find abelian subgroups by finding certain subspaces of F2 to the n, so the vector space over the field with just two elements, which have a certain property. And to do this, we define a bijection. So consider the bijection tau. Now, the tau map is going to be very important. It's going to map the Pauli matrices to the following vectors. I just ordered a second. So this is going to go to 0, 0. This is going to go to 1, 0. This is going to go to 1, 1. And this is going to go to 0, 1. Okay, so what I mean by this is the image of tau 1, tau the identity, tau of x, tau of y, tau z. So this then extends, so this extends from curly P, and now we quotient out by those annoying plus and minus 1, plus and minus no identities. So I'm just going to ignore all the things out front. I'm just going to take pure, if you like, Pauli operances. They're simply sigma 1, tensor, sigma 2, tensor, 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 where the sigma i's are Pauli's. Okay, so that's what I mean by kind of quotienting out by the coefficient. I'm not bothered by what it is. And this is going to go to F2 to the n. Sorry, to the 2n. So this F2 is my notation for the field with two elements, 0 and 1. Where addition and multiplication, so this is a field where addition and multiplication are modulo 2. So for example, if we had tau of, let's say, x, y, z, 1, x, this would be, now I write it like this, in two sets of 5 zeros and 1s, the x is going to 1, 0, so I'm going 1, 0. The y goes to 1, 1, so I go 1, very well, 1. The z goes to 0, 1, so this is 0, 1. The 1 goes to 0, 0. And the x goes to 1, 0. Okay, so this would be the image at the tau of the Pauli. So this the n would be, this would be n. So n would be x. And this would be tau. Now something marvelous happens in this bijection. And it's the following. If we look at the multiplication table, this, what do we get? So let's draw the multiplication table. 1, x, y, z. Oh! So there are all these things, x squared, y squared, z squared, are all identity. X, y, if I'm forgetting about the sign, x, z, if I'm forgetting about the sign, is y, that's z. So let's do multiplication of modulo plus or minus 1 plus or minus 1. Ah! So this is multiplication modulo plus or minus 1 plus or minus I. Okay, so it's forgetting about the coefficients. This is a y, this is x, and this is an x. And over here, if I look at addition, so this is 1, 1. So here, these things don't change. And you can see what's going to happen. Here I did exactly the same table as on the left hand side. Almost there. And if you compare, this is more isomorphic and tau. So it's tau of m times n is equal to tau of n plus tau of n. The multiplicative structure here corresponds to the additive structure over here. So subgroups over here go to subspaces over there. Where are the abelian subgroups? So this is what we need to find out. Where are the abelian subgroups over here that we can then go back and get our so what are the subspaces over here which correspond to abelian subgroups? So subgroups correspond. And to find out where the abelian subgroups are, we introduce a symplectic form on F2 to 2n. So for all any two vectors, I'm going to define a dot product. It's not going to be the classical one, it's going to be the following. So for all u and v, for u and v in F2 to 2n, we let, can I give it a name? No, just brackets. Bracket u v is equal to the sum 1 to n u I. And it's that. And we're going to see that this is exactly what we need to prove to find the abelian subgroups over here. Okay, so this is going to just be in a form, this bracket. Yeah, notice that I've put a plus here. Minus is equal to plus with much better to. But I just emphasize with the minus, you see straight away that it's symplectic, i.e. if we put UU here, we're going to get 0. Now, let's just take some Paulies here. So let's just take n is equal to x and n is equal to y, and let's map them under tau. Yeah, so for example, then u equal tau of m and v equal tau of y. Okay, well, tau, well, actually we can write what it is, yeah? So what is tau of m? Tau of m is x, which is 1, 0, and tau of n, which is y, is 1, 1. So u comma v in this case is going to be this times this minus this times this, which is 1. And if you go through each check here, you will see that you get for single powers, any single powers, when they anti-commute, i.e. when you've got the x's with the y's and the so so tau n comma tau n is equal to 1 if and only if m and n anti-commute. Okay, so I'll give you an example here of an x and y, but you can see straight away that if I, for instance, take one piece to give you identity, I would have a 0, 0. So this would be a 0, so obviously they commute. If they're the same, then it's symplectic. And then if they're different, so you only have to check them in a different, and you see these different ones here, will always give you 1 when you calculate this symplectic form. So this is if there were just single powers, but what happens if we had, what would happen if we had ones on n? On m qubits? Well, then we're going to get a 1 in the sum. So on n qubits we get a 1 in the sum of tau n tau n. So here we get a 1 if and only if, so it's in the j term of sum of this, if and only if the Pauli's in the j position anti-commute. Okay, so you see that it's basically saying exactly the same thing, except now I'm taking position by position for operating on n qubits. So that means then that if to get these, so these m and n to commute, so these m and n commute, I need an even number of anti-commuting things. But an even number, this is all elements in 2, so an even number is just 0. And an odd number is just 1. So in fact, I have proved that this is true. This is always true, whether we want 1 qubit or n qubits. Because everything's 1 and 2. Do you see that? I can see nobody today, so it's a bit difficult for me to judge any reaction whatsoever.
Yeah, makes sense.
Okay, thank you. Yeah, so this is just extrapolating. So now we know what to do. Now we know when we want to find out things. We need these things to always be, if we take any 2 vectors in our subspace here, we need this to be 0. So abelian subgroup let's just write abelian subgroup. And there's some person where we usually call these subspaces C because they're columns. The subspace is C for all you in C. So abelian subgroup, this corresponds to subspace C of F2 where U comma V is equal to 0 for all U and V. Brilliant. Okay, so let me look at an example first. So before, still got a lot of work to do because we want to know, for example, where's the centralizer here. But for the moment, let's just have a look at an example and see. So now I'm going to describe our stabilizer. So normally with stabilizer page, you get a matrix. So a stabilizer code. So we usually define C by a n minus k times 2n matrix whose row space is C. Okay. And that's called a generated matrix for the code. Okay, so the rows are just the basis. See? So the ith row, ith row, let's call this G of G is tau of n I for some generator of an abelian subgroup S. Where the C is tau of S. Right, an example. Yeah, so let's have a look at what happened here. G was okay. So let's say they took this G. Now let me write down the A's first, and then I'll convince you that this has this property. Okay, that in a more general sense, general way. So this would correspond to the N's. So N1 would be X, Z, 1, 1, Z. N2 would be ZX, ZX, Z1, and you see for the constructor, the other ones are just cycling round. So just as And you can check by simply comparing the two things here that these all commute. But that's not a surprise because I will now show you why, in fact, anything. So if G has the form I, so instead of checking this thing, pair of rows, pair of rows, I'll do something far more impressive. First, I'm going to change my ink. Oh, I can't get it off. Ah. Hold on. Well, whilst I'm doing this, you can check. Let's say we have this. So in this case, this is a 5 by 5, so this is n by 2 matrix. N by 2 matrix. Then let's work out exactly what the condition is that that we have to go here. So U equal V is sum of UI VI capacity, VI UI capacity. So that was how I thought.
Is there, like, what if there's a mistake in that? It's like for G, like we have a 0, 0, and then you wrote like the last. Oh, yeah, okay.
I'm changing this to J's here just because I want to use I. So let's work out, because this is for any two rows. So for rows U and V of G, we want U comma V is equal to 0. And that's enough, right? I mean, once we have that any two rows are orthogonal with respect to this symplectic form, then any linear combination of the rows will be 0 with respect to this form. Okay, so therefore any two vectors in C, the row space of this matrix, will have this property. Okay, so that's what we want. This is the special type case that K is 0. I'll come back to that. I just want to prove to you for this example, there's a very good reason why this works. So if we take U to be the ith row, and so U is ith row, and V is the other row. So let's start working with these. So for this general case, U comma V then would be the sum of Uj, that's the ith row, okay? So that would be simply Gij, Gij. V is the nth row, so that's V, that's GL, comma, J plus N, minus GL, comma, J, GI, comma, J plus N. And that's summing of the J. But what's Gij? That's just delta of J. So this is the sum of I would be equal to J, so this is going to be 1, so that's just G of L I plus N minus, and likewise here, this GLJ is 0 if it is delta LJ. So this is minus GI okay, so there's no time, yeah, because now the J's is gone. But what is GL of I plus N? Well, that's A of Li, and here this is A I L. And now you see why this is always going to work. So this is zero, but also this is always zero. So C, so UV 0 to 0 for all, UV is C, if only if A is symmetric. Which is why this works here. Now that's a very quick way of making stabilizer codes. Yeah, I mean, all we have to do, write our density matrix, a symmetric matrix, and we've got a stabilizer code. So this gives us a very quick way to construct abelian subgroups S of size 2 to the n. Okay, because we have n generators. Well then, but this is a so these give n zero something codes. And so of course the zero is not really very interesting, but you can take any subgroup. Taking any subgroup of S. Any subgroup of size 2 to the n minus k will give a n k. Okay. What is even more amazing is the other way goes round as well. Okay, now that I will prove to you today, and that's not in any book, so I don't know if anybody realised that, or whether that was just me this morning. But I think it works the other way around as well, as we shall possibly see within the next half an hour, if I don't find a mistake along the way. But the first question is this dot? What's this minimum distance? How do we work out our minimum distance in the binary code setting? That's what we have to do next. But I need a drink of water first. I'm a little break.
Right. You said that like all the codes in this way can be brought back to like an INA matrix. Like, is that the?
That's my rash claim, Adrian. Yeah. It may well turn out to be complete nonsense in the next half an hour, but I think so. I think so. There is always, for any stabilizer code, I can't believe I'm going on the record and saying this, because I'm going to have egg on my face in about half an hour. But yeah, I mean, certainly this is so far so good, right? We certainly have a very quick way. So once you've got this subgroup, you can just make any subgroup of this subgroup, and it's going to be a big and this is going to give you a stabilizer code. Right, but first things first, we need to, and actually this is going to be related to what I want to do. We need to work out what this minimum distance is in the binary code system. Right. Yeah, so I don't know if I'm going to mention this now, or I'll mention that later. No, I don't. So let's mention it now. I won't put it on the board. I mean, a symmetric n by n matrix, if you'd taken my combinatorics course last year, you'll be shouting simple graph. Okay, so, well, simple graph. I mean, there could be ones on the diagonal at the moment, but we'll see later that even that is not necessary. So this is actually just given by a graph. And so there's A is given by a graph. On inverse C. And in the previous example, it was simply the cyclic graph on 5 vertices. Okay, so it's just well, given by it's the instance matrix. Well, in fact, we did this in discrete mathematics, right? All those many years ago. So it's just the instance matrix of a simple graph. Now, you could say it could be with loops at the moment because you could have ones on the diagram, but we'll see that that's even that we can get around. Okay. So in fact, it's going to be just a simple graph. So we saw that D was the minimum weight of the elements in the centralized limits of S. So what we want to do is find out where the centralizer is. So let me think. So we have that tau of S is equal to C cosine where C is a subspace. Now things commute, so commutes M commutes with S. So but well, N commutes with N if and only if this. So now suppose U is equal to tau of M, then V, so then N is in the centralized element S. UV is equal to 0 rho U in C. And that's it, right? So we're thinking so to find these tau n's, where it's the centralized point, we need to find the vectors V, which are going to be 0 with U, and we do the symplectic product for all U in C. Okay, so M commutes with N, over in the Pauli world, we decided it would only if tau n is 0. So now if we take n in this and n in the centralized, this is going to be 0. And if and only if.
Wait. There's two u's there? Like, is one of them supposed to be a v, or like for all u in C, and then since u equals, or wait, what's the v then?
So yeah, v is tau n. Yeah, I didn't like this one.
Okay.
Yeah,
okay, then yeah.
Let me look at my sheet. I didn't bother. I just thought it was so obvious.
Sorry.
No, yeah, so anything commute if only this, right? So we want to find things that commute with the elements of S. The elements of S get mapped to C. So we're looking for the elements to commute with all of which have this with all of C. So if we define C per A, so we can't use C per because that means something else. That's the capital normal orthogonal inner product. So this will be the V in F2 to the 2m such that UV is equal to 0 for all U in C. So that then tau is centralized over this. Is equal to 0. Okay, so that's because we're looking for the stuff that commutes with all the elements in the S. And commutation here, so things commuting, yeah, because of this. Right? So this follows from this. Okay? So M and N commute if and only if the tau of the theta is different. So where has the centralized gone? It's gone here, and likewise the centralized tau from -1 of C per A.
Wait, what does the A subscript mean? Like it's orthogonal sub A? Or?
Yeah, it means that it's orthogonal with respect to this bracket.
Oh, okay.
Yeah, that we saw before. Because I don't want to just write orthogonal.
Yeah, because we wouldn't know what.
Because the orthogonal is the normal dot product U1 V1 plus U2 V2 plus yeah, which actually appears and will appear in various exercises. Okay.
Okay.
Okay. So now we need to find out what the minimum weight is. So the minimum weight was the minimum weight in the simplified stuff S, but it's not quite that easy to see. So let's leave that for the moment. Tau is this. So we have this, and recall tau of F is C. And this makes sense, right? Because C is a subspace of C per A. Yeah, it's also true that U probably is equal to 0 for all. So it's certainly true that this contains C. So we thought that was the minimum weight, but where should we recall that we did 1 x, y, z under tau went to 0, 0, 1, 0, 1, 1, 0, 1. So when I'm calculating the weight, I want to calculate the weight when this should be 0, this shouldn't count, and all of these should count. So the symplectic weight, so the SWT of U1 up to U2n is equal to the number of the sets I in 1 to n, where ui plus is equal to 0, is not equal to 0. Okay, so these are the only things that don't count towards the weight. because the x, y, z count. And so the d now we know is equal to the minimum symplectic weight of the elements of C per A, not C. Because we have to take out, which is equal to the weight, minimum weight. Now, this will be the case when k is not equal to 0, of course, because if k is equal to 0, these two things are the same, these two things are the same. So k is 0, we have to do something. S is equal to centralized S. And that, well, that now you see because the dimension, so look at the dimension of, maybe I should look at this here. This is, you can see this, the dimension. So in this case, okay, so they're all equal, we just put D. And the reason for that is because that's kind of like where we're aiming for when we take our subgroups. Okay, so when we take our subgroups, the centralizer, so let's just see, but now we know all the dimensions and the sizes and everything because we know the dimension of C per this thing. This is just an orthogonal subspace. So since dimension of C is equal to n minus k, we know that the dimension of C per A is 2n minus n minus k. Which is equal to n plus k. Okay, so that means that when we take our subgroups, maybe if we took our subgroup of the case k is 0, like in the example, then the centralizer would get bigger. Okay, so suddenly you've got more elements in there, and it's possible that the minimum weight drops. Okay, but anyway, it's a good indication of where you should be aiming for. So this is I think it's the right definition, definitely. Is it my imagination that has the colour changed? Or is it just running out again? I've just changed it so it shouldn't be. It looks like it should be black. Anyway. So now I want to kind of like go. I've still got to be fault tolerant, which is going to take at least 40 minutes. So I'm going to give myself 10 minutes to try and convince you that, in fact, everything comes down to price. Now, this is what I read this morning. So, yeah. So let's just observe something. So this is a. What happens here if I replace VI plus N with VI? So if I replace this here with VI plus VI plus V, and then UI plus Absolutely nothing, right? I mean, all I've done is I've added something to take the same thing, so nothing changes. Agreed? And likewise, I could have done the same to the first one. Nothing changes. So that means that it's in the sense that it's still commuting, right? So we can replace. I mean, when I say anything up to it's up to so we can replace the I plus column of G with linear combinations of these columns. Okay, and it's still going to have the same orthogonality property. We can also do Gaussian elimination, Gauss, apply Gauss, which just changes the basis. Changes the basis. Stick, i.e., finds a different set of generators. Correct? Okay, so if you're just changing the basis by doing row operations, all you're doing is finding a different set of generators. And you can also do this column thing as well, which doesn't affect the orthogonality. Now that might change the thing up to some kind of equivalence, but it's still an equivalent thing. Yeah, I think that's a fair equivalence. And doing this, and then before we do that, we can also add things from this into C, and these are all commuting with each other. So yeah, so if we do it one by one, you start off with a code, take something from the orthogonal C per A, okay, add it to C. Now calculate your new C per A, the dimension will go down by one, and you just do it one by one, and you get all the way up to, so step by step we can go from step by step, we can take a vector from C per A and add it to C to make a larger subspace. And get a large subspace and get to a subspace. Now, this n-dimensional subspace is given by n squared matrix, which if we did this kind of replacing the I problem by linear combinations and then doing row operations, we can get it into.
This is assuming that they're never equal, right? If you can, because you need to recalculate the orthogonal subspace every time. Because
Yes.
Once you add a new vector, you can't add the old ones.
Yeah, that's why I said step by step. You're going to do my vector recalculating C per pen each time.
And are you going to do that? You can always find a new one, like a new vector that's part of that's orthogonal to everything.
Because the dimension just goes, so you start with n minus k, n plus k, n minus k plus 1, n minus k minus 1.
Oh, all right. The dimension of you're guaranteed that the orthogonal subspace is going to have the complementary. Okay.
Yeah, you know what the dimension is. So, yeah. Yeah, so in the end you get to there, and then you can get, so, divided by G's I and A. I mean, it's up to some kind of very broad, well, not that broad equivalence, but to some kind of equivalence, because this will, yeah, preserves your thing, but really changes your Pauli's in that coordinate, but in some kind of, but you're just doing a permutation. So up to a permutation of the Pauli's in a coordinate, in each coordinate. You basically get all the way to here, and now we can refine and somewhere, so which defines an abelian subgroup S, which has the initial S prime as a subgroup. Yeah, I think that works. Yeah, so I didn't find a mistake anywhere there.
You're guaranteed that A is symmetric?
And you're guaranteed A is symmetric, because we proved that already.
All right, okay, because it's all right, because you know it's abelian, so it has to be.
Yeah, so it's crazy, but I think that's right. I don't see anything.
Anyway. You can do Gauss, then you can get.
Yeah. So I think maybe this will make a nice thesis for somebody here, just to study. Because I don't think this has been observed anywhere. I've not certainly seen it. So these graphical examples have appeared because what they do then is they make these graphical ones, and then they build on those by taking cosets to make non-stabilized curves. So you make a direct sum of ones starting from a graphical matrix here, and then choosing certain cosets. Certainly well chosen. Certain cosets allow you to make your subspace QS bigger whilst either maintaining or almost maintaining the minimum distance. Okay, so they have been looked at, but I don't think we realize that in a way they describe all stabilizer codes. I think that was all right. Now,
it seems weird that no one's it's not, but it seems like a natural question to sort of ask if what you're doing includes all codes, or if you're missing out on.
Yeah, well, it's up to some kind of equivalence, as I say. When I do this, I'm allowing permutation of the Pauli's in things. So up to permutation of the Pauli's in a coordinate.
Oh, okay. Permutation within. Wait, what does that mean?
It means for all the elements of S, if you on the third qubit, say, for all the elements in S, you do a permutation on those Pauli's.
Oh, like circular.
Yeah, is there a special permutation? Yes, it's a special. It's the permutation which leaves the identity and either cycles around X, Y, Z, either that way or that way.
Okay.
Okay. So you're up to that equivalence, because of course that doesn't change commutativity. If you do that in every single Pauli in your subgroup S, as a third coordinate, then
and it doesn't change the properties of the code, like the NK, the.
No, nothing.
Okay, so so it's not exactly all of them, but they're just as good as everything else there is.
Yeah, so up to that equivalence, everything comes down to a graph. So what would be interesting then is, can you see from the graph what the minimum distance is?
Can you?
Well, I think so. Well, you can certainly see what the weights of the operators of S are, because the operators of S correspond to subsets of the vertices, and then the weight of that is going to be the sum modulo, so taking the size of the neighborhood of those vertices modulo 2. Yeah, so if one vertex is a neighbor of 4 of them, then you don't count it, yeah, or 2 of them. Yeah. So it's the neighborhood modulo 2 will give you at least the weights of the elements of S, which of course For the graphical ones is the centralizer. So yes, that will then give you them. So you'll get the middle way of that. But then how do you, so where do your subgroups correspond from? This is really interesting. So your subgroups will then be, you want to kick out certain elements. So certain elements are certain subsets of the vertices. So you say, I now define my subgroup as this graph minus these subsets of the vertices. And then then what's the now I don't know what the weight of the centralizer is, but it's a that's why you do the project.
But Simeon,
Yes.
you can only think about the graph if it's an n per n matrix. Like if you are working on a smaller subgroup, it doesn't make sense anymore, right?
Well, that's the point, though, Edgar. So we start off with the smaller subgroup, okay, and then we extend the subgroup to a bigger subgroup by taking vectors from here and adding them to your code.
Yes, but like given the n per n, like the n-dimensional subspace, if you think it as a graph, when you like you cannot study the subgroups of that like via the graph. Because like why could you?
I think you can. I think the subgroups are simply taking out subsets of the vertices. So you define, So how do you get? So your subgroup is the whole thing, right? Generated by any subset of the vertices. So basically, that you're thinking of the vertices now, as now labeling the rows. So any subset is just a linear combination of the rows here, which is an element of the subgroup. So if I want to now find a subgroup, I throw out somehow. I think that works. But there's not a subgroup that you say.
But the graph doesn't make sense anymore, right?
Well, the graph's still there, but the graph, so let's say you wanted a subgroup of size 2 to the n minus 1. Then it would be all combinations. So you might say, well, I'll take out a certain element. I mean, if it was just a simple row, it would be just delete a vertex. So you would just, if it was just like taking out a row, you just delete a vertex.
But if you want to delete a vertex, you have to delete a row and a column.
Yeah, I know. So you still have to leave the graph there, but you just have to say, okay, I'm taking, I mean, can you see that you can still describe?
Yeah, okay.
It's hidden somewhere in the graph.
Mm-hmm.
Yeah, I mean, I only thought about it this morning, so I don't
Okay.
I don't have time to think about it yet, but it seems to me that all is fair enough. Anyway, let me get on. Let me get on and talk
Will
about
the graph still, will it still describe like a commutative subgroup? It's like you've just eliminated.
I mean, the subgroup, the big subgroup, all you've done is you embedded your subgroup in a bigger abelian subgroup, which
but like when you eliminate the column.
You don't eliminate columns, you eliminate combinations of rows, because it's the combinations of rows which you accept.
No, but like once you work on the graph, you want like study subgraphs.
No, I think you don't study. I don't think it's exactly subgraphs, is it? It's because as Edgar points out, you still need, you still got an n minus 1 times n matrix here. So
okay, okay.
So graph, which is vital to your subgroup.
Right, like you can't if you lose the column, like to make it square again, you lose important stuff.
Yeah. In fact, it would no longer be necessarily well, unless you actually deleted the same row column, it wouldn't be symmetrical. Gosh, interesting stuff. Anyway. maybe someone did think of it before, maybe it's hidden somewhere, but it's certainly not in Niels number 12. Okay, so let's try and finish 10 essays. So as we've seen that our quantum error correcting codes from now on, if I ever write this again, I should write QECC, because it takes some time to write. Allow us, so protect not only stored, transmitted, quantum information, but it also protects the information as it undergoes some kind of dynamic undergoes computation. Okay, so we can use it to protect our to implement our computation in a what's the word? In a way that protects against faulty logic gates. So that's going to be the idea. So the idea is we can we go into the quantum circuit. With faulty logic gates, providing probability. Is small. Okay, so we need a small error, but these quantum error correcting codes will allow us to do this computation. This is the idea behind fault-tolerant quantum computation. Now, so we suppose we have encoded our quantum information. So we thought before, I think we last time, that we could encode, for example, with the shortcode 1 qubit onto 9, with the one examples of before, 1 qubit onto 5, and then we talk about 2 logical bits. We have 0 logical and 1 logical. And for example, 0 logical and 1 logical. And now we want to apply some computation. So what we could do is decode it, apply our gate, and encode it. So to apply a gate, we could decode, apply the gate, and encode. But what we're not able to do is apply the gate to the encoded bit itself. Because the problem here is but then the information is only protected before and after the gate. So what we want is a way of applying the gate to our logical bits in a fault tolerant way, in a way that the probability is not. So in fact, what we're going to define as fault tolerantly is if the probability of something going wrong is p, we want the error to be p squared or some constant times p squared. Okay, so that's going to be the idea. Now let me give you an example. So let's just consider the code we saw right back at the beginning. The code 0 logical, which was just 0, 0, 0, and 1 logical, which was 1, 1, 1. Now this only protects against X errors, no? It doesn't protect against which protects against X errors. But in a minute we'll see a bigger example which protects against all poorly and therefore all the continuum of all errors. And suppose we want to apply a C naught. So how would that work? So what would a C naught do? A C naught would take 0 logical, would go to 0 logical, 0 logical. So let's see all of those bits. So one way to do this, we could do. So bear in mind now we have 6 quantum wires. Okay, so we have 3 wires coming in here, corresponding to our first logical bits, and 3 more down here corresponding to our second logical bits. So I'll just do that to indicate the fact that these are encoding bits. And what we could do is simply go, okay, we'll do this. This would imply, this would do it, right? No? I just lost interest.
It's bad.
This is not good. This is not good because an error here, is. So not full. So if you want to make the error, because an error there on the first wire of probability occurring P will then transfer to the other 3. But of course, you already know what to do to make it fault tolerant. So we just make it fault tolerant by and now if I were here, I then put recovery back. Yeah, so that was the R from our error correcting theorem. Afterwards, what's the probability that we go wrong out here? Afterwards. Because we could protect against one, well, X error here, okay? So if something happens here, and we apply the recovery map, and it goes back okay, unless 2 errors have occurred. Okay, so our probability of error here is now order p squared. So this is fault tolerant. Okay, so that's basically the argument. And of course, in this case, it's very easy to design a fault tolerant C naught. But in general, it's not. It's a as we shall say. This is not such a user.
And then it'll depend on the code too, right? So like some can be more easier to make fault tolerant than others.
Mm-hmm. Exactly. Right. And also it depends on which gate you want to implement and what's I mean, it's a whole business. It's a whole business. Fault tolerant. So let's look at a proper code because that's as we know that's not the fault correcting code. Which could, I don't know what this is. I'll leave that at the moment. Okay. So let's look at the proper code. So this is from exercise 6.10. Oops. We'll see that this steam code is a 7, 1, 3. Great. And you may wonder why we will bother with a 713 code when we already saw a 513 code. And the reason is because it has very nice stabilizers. So M1 here is X, 1, 1, X, X, 1, X, 2, 1, 1, 1. I'm now worried about what I said before. I'm looking at this phone. If you think about, another thing on my face, I think. If you think about the iterator matrix here, this has got a huge 0 down. This has got a 0 that's all the way down here on the bottom left-hand bar. But then I claim that I could then add those things, add the column and the column by doing the commutation of the x, y, z, and all these y's and x's, and maybe it's still true. I don't know. I mean, that's why I would like somebody to think about it. Okay, so it's got these nice x's and x's, and I was thinking it's a very neat and very good code to implement because it's very simple. These x's and z's. And that's partly what exercise 6.10 is about. Right. Now, yeah. Let's first see if we can find how much time I've got left. Not that much. What I want to prove to you is that I can find a nice basis. Okay, let's do the basis first. Let's find. I want to find out a 0 logical and 1 logical. I want to find a nice basis. Okay, and the way to find a nice basis here will be the following. Sigma 0 is going to be 1, 2, 3, 4, 5, 6, 7. Okay, because there's 7 qubits here. And this has got to be stabilized by all these elements. So if it's stabilized by M1, then this particular element of the canonical basis gets mapped to 1, 0, 0, 1, 1, 0, 1 by this M1. This thing gets mapped by M2 to this. So you need at least all of these things and every single combination of these M1, M2, M2, M3, M1, M2, M3, so all 8. So you're going to get 8 strings here. And if you write them down, now I've done it in a different order, but anyway, you get these 8. Okay, let me just quickly write this down. we got one. Finally. I think that could not be. Well, I copied this. I copied these out from somebody else. Maybe they had a different order. That's possible. That's possible. In which case, mine might have correspond to theirs. So let me do it on this paper. Let me just do it just by looking at this. Yes, so it should be. Do we have this one? 101 should be this one. 1010. Yeah, no, it's not. So these are. Oh dear. They must have had a different. They won't make any difference. Okay. Okay, well, so this is going to be 0, 1, 0, 1, 0, 1. This one is going to be 0, 0, 1, 0, 1. And then these two are going to be 1, 1, 0, 0, 1, 1, 0. 3, 1, 0. This two. Okay. 0, 1, 1. Okay, so these are and this is zero logical now. So if you apply any of the combination of these things, they just get commuted round. And if you apply any of the sets at the M4, M5, M7, since any combination of these, and any combination of these commutes with these things, they always coincide with the even number of the ones here, where the z's are. So the z's here would kind of correspond to the infinite ones. So this is then fixing the signs as well. Okay, so zero logical. This is in our basis.
Wait, how did you calculate the? Like, how do you get from the m's to the? From which m's do you get sort of the 0, 0, 0?
I started with an element in the computational basis, with all the zeros.
Right.
And I applied all the different m's to that. Okay, because
you apply all possible combinations of M1, M2, M3.
Yeah.
Okay.
And now I claim that this. I mean, now you probably still have to check because it's possible that it's now you need to check. Now you need to check that M1, M2, and M3 really just commute these things round. Okay. But I'm going to leave that to you. Yeah. So just take this one for example, and apply this. This goes to 1, 1, all zeros, and then 1, 1, 0. Which is someone, is it? This one. Yeah? So you better then check that M1, M2, M3 really do commute these things around. So this is stabilized, but it is. Okay? Now, let's suppose we've got some M in the centralized S. What happens to this N? Let's say N. Okay, so what happens to MIN of, let's say, D? Then since it's in a centralizer, the n and the mi commute. Since zero logical is an ideal space of eigenvalue minus all things in n, let's just say, let's do this. So this means that n times zero logical is also in the graph. Okay, so once I've got one element, I can generate the rest of the basis just by finding the elements in the centralizer, which are much easier to find. Okay, so that's a general trick. Okay, so you've got, if you take something in the centralizer and apply it to logical, then you'll also still be your stabilizer. So now we need to find something in the centralizer. Let's observe. So let's observe. Yeah. I need space. Observe x, 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 x is in the centralizer. Okay, so this commutes with all of those because these have all got 4 x's and these have all got 4 z's. Okay, so the x is what doesn't matter, and then since these have got 4 z's, it commutes with all of those. Yeah. So this means that, so let's call this x tilde. So x tilde of 0 logical, I'm going to define as, so let's 1 logical be x of 0 logical, which effectively changes all the zeros from 1, interchanges all the zeros and 1s here. Okay, and that gives us a different vector in our QS. So we found a basis for our QS. And so QS has a basis 0 logical, 1 logical. Okay, right, if I 1 logical, I get my changing all the zeros and ones over there. Good. Also, then, but observe that x twiggle is x on the 0 on QX. Okay, so if I just think about this as a simple qubit, then what's this doing? X of 1 logical is going back to 0 logical. Anyway, that's just by applying x logical to this equation, x tilde, if you like, x logical to this here. So this tilde will be the logical. So where's z logical? And in this case, but it doesn't always work like this, so be careful. Yeah, it's a very, very special chemical scheme. Also, z logical is in fact all the z's. Now again, this obviously is in the centralizer because it commutes with all of these. It's obvious, and it commutes with these because there's 4 x's for those. So it's in the centralizer, and really it does the same thing. What does it do here? To 0 logical, if you apply z's, all of these got an even number of 1s. So when you apply z's to all of them, nothing changes. Yeah. So z logical of 0 is 0 logical. Whereas 1 logical has all of these zeros replaced by 1s and all the 1s replaced by zeros. So all of these have an odd number of 1s in 1 logical. So when you apply z logical, you get z logical of 1 logical is minus 1 logical. Isn't that amazing?
Wait. Oh, right, because it's 7.
Huh?
No, I was counting 8 instead of 7. Yeah, okay. Never mind.
Yeah, so that's good. So this is a very nice. So now we can do our quantum computation. So of course, C naught on our 7 bits is exactly what you picked. I don't know if I need that anymore. I don't think I do. Okay, so I'm going to get rid of this. I don't even think I need my 0 logical anymore. So I'll just take a bit of water and I'm about to delete the top half of the board. But this trick somebody might need to do there to find the basis of the quantum mechanics. Okay. So obviously a C naught we can implement very easily, right? So for a C naught, so a fault tolerant C naught would be will be this one. So this would be how we implement the C naught here. Because again, if the x is 50 and x on equals equal 1. Okay, so there you get the C naught, fault tolerant C naught. Now, what about if we put something a little bit more complicated? So let's try and work out what happens if we wanted to implement, let's suppose, following circuit, which is not logically, just normally we'll just do this. Okay, so I'm the first one I see. Okay, but you want to implement it and solve fault tolerantly. So how is, so we will need, if this is going to be a logical bit coming in here, we're going to need H logical. So first thing is we have to work out what H logical is. Right. Now you think you know what it is, and it turns out you're going to be right. But let's yeah, so let's define H as H like this. Now I don't know if I want to do this. Okay, so since H and H is equal to X, we have H logical, H logical X logical. Okay. Why have I done that? Okay, so I'm trying to work out what H further zero logical is. Then I say, okay, yeah, this is equal to zero logical zero. Seem to miss something out here. So from this, it's implied that I can take this H squared on the other side, because H squared are all like identities, yeah. So then I have this. So I'm just trying to work out what is. So let's I'm trying to prove that this is happening, okay? So let's suppose this is A logical, plus B1 logical. Then we know that So this is going to be equal to x times this, but x just is takes us to this. So A is equal to B. And now H1 logical is equal to, let's say, C is 0 logical plus B logical. Yeah, so in the one logical case, so if I change this to a 1, this is a 1, and this is a minus 1, because then it's, so 1 logical is minus 1 logical, so then this is minus x of 1 logical. So here I can, this is then minus d0 plus minus c 1 logical. So c is equal to minus. So by normalization, we have exactly that H is Hermitian logical. Okay, so that was the proof that this H I divided here, this H logical is really this. Okay, so I'm just proving that it really is the Hermitian. Okay, so that is an exercise. So to implement this H here, let's do it up here. So this is the C naught. To get the H then, all I need to do is put H's all the way down here. And that implements the H logical in a fault tolerant way. Okay, because you need like many of us to be able to really mess up in fault tolerant things. So this is a fault tolerant, and this is a fault tolerant Hermitian. Yeah. Okay, you just have to put H's all the way along the 7 class. Okay, so let me just finish with a fault tolerant. So I wrote a condition, but I meant Panama. So all of that was just to prove that this H tilde really was the Hadamard thing. And now to do this thing fault tolerantly, you put in your 0 logical bit. Sorry, you put in 0, 10 to 7, 0, 10 to 7. You do fault tolerant prepare your fault tolerant prepare 0 logical. So you have to work out a fault tolerant implementation of your to get onto your logical bits. Then you need to be able to fault tolerantly do your recovery. So you fault tolerantly correct. And this seems a bit strange since you've only just prepared your 0 logical. But even preparing just a period of time, that will decode here and errors will propagate. Okay, so you always have to keep putting your fault tolerant correct back in here. Now you can do your fault tolerant Hermitian, which is here. So you do your fault tolerant Hermitian, so Hadamard. Your fault tolerant Hadamard, then you do a fault tolerant correct. And a fault tolerant correct again here, because it may well have been that state of time have decoherence. Now you do your fault tolerant C naught, which is this bit here, which really is this implementation. And now you do fault tolerant correct again. And then finally, to finish, you have to do a fault tolerant measure as well. So you see, the whole world of fault tolerant quantum computation is complicated, and you could write a book just on that on its own. So, but I hope that very, very brief introduction at least explains what the problem is and how you go about how to solve it. Okay. So stop my